Hello, Maurits here, and this time I will talk about a related rate of change. And a related rate of change is simply how something varies with something else. So for example, we could have, say, a cone-shaped container of some kind, and we fill that up, say, with a liquid at some certain rate. And we want to know, say, that is some rate, so change of volume over change of time, and we want to know how, say, the depth of this or height is changing as we pour in the liquid. The rate of change of the height versus the rate of change of the volume. So, say we call this R here, and we call this H, right? So we have a radius and height of the part that is filled. And to find the relation between these two, we start with writing a formula connecting these, the volume and the height in some way. In this case, it would be radius here too, but we'll fix that later on. So we have that the volume equals to a third times the base, which is pi r square, times how deep we have filled this, so that is the height. And the next thing we do is take the derivative of this with respect to t. And remember now, both v, r, and h are functions with respect to t. So the first we get that is the v dt equals to, write this as pi over 3. And now we have to remember that these two are functions, both of them are functions of t, so we must use the product rule for these. So that will be then bracket, so we use the product rule, right? So bracket 2r times the inner derivative. Remember this, we did previously with implicit derivatives. So r prime, I mean by the prime here, derivative with respect to t, times h, the derivative of this, keeping that, and then keeping this, times the derivative of that, which is h prime. So this is an expression relating this one with actually these two, but mostly we are only interested in relating it to one of them. And we can give an example here. First I give some values, but we will make a formula anyhow, and then we will plug in the values. So say in this container has a height, total height, of say 10 centimeters, and say it has a radius, I write capital R for the complete thing, of say 5 centimeters. And since for a cone, this divided by that is this divided by that all the way through, right? It's basically a linear relation. We can say that our radius divided by the height at a given moment equals to the radius of the container divided by the total height of the container, or r equals to r over h times small h, right? Now we can take this and plug it into this to get that our volume equals to pi over 3 r over h squared times the height, which we can expand to pi over 3 r square h square, that is capital H square, right, h cubed. Okay, so now we have an expression. We could work with this one and do plug-in stuff, but it's easy now to first do this and then take the derivative. Okay, remember now that this is a constant, so that makes it very easy to take the derivative of this with respect to t. So we get the rate of change of the volume equals to, keep the constant, pi over 3 r square over h square times 3h square h prime, right? Because we have outer and inner derivative. we can see immediately that we can make a little bit of simplifications here, right? The 3 there will cancel against the 3 there. Okay, so we have now the expression dv dt equals to pi capital R square capital H square h square h prime. That will relate the change. We can write that just for the sake of it. We'll write that as dh dt. So now we have an expression that relates the rate of change of volume, the rate of change of the height, with the height we have. And suppose we want to know the rate of change at a particular moment and for a particular flow. So say that dv dt equals to, say, 1 cubic centimeter per second. And that, what more? Let's see if we've done everything right. Yes. And that, yes, and that, say, the height at that given moment we look for is 2 centimeters. Okay, so let's plug that into this thing. We know that this here is, so let's write it down here, or actually I can write it here. This is 1, right, equals to pi 10, no, sorry, radius 5 square over 10 square times h square, which will be 2 square, times dh dt. We can cancel a bit here because 5 square times 2 square is 10 square. Okay, so these two will cancel against that. So in this case we get 1 equals to pi dh dt, which means that our rate of change of the height with respect to t, if we have a inflow of 1 cubic centimeter, that would be cubic centimeter, of course, cubic centimeter per second, units, and the height is 2 centimeter, will be 1 over pi centimeters per second, right? And that will solve the problem for us. Okay, thank you.